Welcome to this explainer. Today, we're diving into the absolute bleeding edge of AI integrations, the Model Context Protocol, or MCP for short. As AI moves from just generating texts to actually executing real-world actions, our old-school security frameworks are frankly falling way behind. So we're going to crack open a highly detailed research paper today, and my goal is to cover everything inside it so we can figure out how to lock down this wild new frontier.
This quote perfectly captures the double-edged sword of modern AI. MCP essentially gives these models hands to interact with the real world. They can query your databases, pull live data, run scripts. It's like a giant leap forward for enterprise software. But here's the catch. Traditional API defenses, they just aren't built for a system where the AI writes its own rules. And as the researchers point out, this opens up some truly terrifying new security vulnerabilities. To cover everything in this dense research paper, here's our agenda. 1. Understanding the MCP architecture. 2. The MCP threat landscape. 3. Server-side mitigation strategies. 4. Client-side security controls. 5. Securing multi-server deployments. And finally, 6. Challenges and final takeaways.
Section 1. Understanding the MCP architecture. Okay, let's establish exactly what we're trying to secure here, because you really can't protect a system if you don't understand its moving parts. So the Model Context Protocol was introduced by Anthropic as a standardized framework. Think of it as the bridge between static AI models and dynamic, real-world data. Instead of hard-coding custom integrations for every single AI app you build, MCP gives us a universal standard. It's the connective tissue that lets an AI model literally say, hey, I need to check this customer's live billing history and actually go do it securely. Now, this core architecture relies on three main components working together. First, we've got the MCP host. This is the AI environment itself, like Claude Desktop or maybe an AI coding tool like Cursor. Sitting inside that host is the MCP client, acting as the middleman. And finally, the MCP server. This is the gateway that actually exposes external capabilities to the AI. We're talking tools for executing tasks, resources for accessing data, and prompts for reusable templates. Every single secure request has to flow right through this triad. Moving on to Section 2, the MCP threat landscape. Now that we know how it works, we've got to look at how it can be attacked. Because MCP is so incredibly dynamic, the threats are vastly different from your traditional web apps. Just think about it for a second. If we give an AI autonomous, or even semi-autonomous, access to external functions, what happens when a tool is compromised? It's not just a bad data point anymore. We're talking about catastrophic system-wide failures, unauthorized data exfiltration, or even worse, an attacker setting up a covert command and control channel right under our noses. Take a look at how the MAstro framework meticulously categorizes these threats across every single component of the architecture. The researchers mapped out 7 distinct layers here, going from foundation models at layer 1 all the way up to the agent ecosystem at layer 7. If you look closely at the MCP server column, you'll see severe threats like denial of service, data leakage, server spoofing. And then, over under tools, you see something entirely new, tool poisoning. Every column on this board represents a specific surface area that security architects absolutely have to lock down. Standard API security practices like preventing insecure configurations or DOS attacks are necessary, for sure, but they just aren't enough anymore. We now have to worry about unique MCP risks. The most critical one? Tool poisoning. This is where an attacker maliciously crafts a tool description or its parameters. See, because the AI model reads these descriptions to figure out how to use the tool, a poisoned description can literally trick the AI into executing harmful operations, completely bypassing traditional authentication. Wild, right?
Section 3. Server-side mitigation strategies. To fight these advanced threats, we really need a robust defense-in-depth framework, and that starts right at the gateway.
Protecting MCP deployments requires a comprehensive multi-layered defense-in-depth framework from end to end. Security isn't just slapping on one firewall and calling it a day anymore. It's this complex combination of network segmentation, continuous session validation, host security monitoring, and strict output filtering. The whole thing is designed so that if an attacker manages to breach one layer, boom, they're immediately stopped by the next one. The paper outlines 5 critical server-side controls to make this happen. First, you need strict network microsegmentation to contain any lateral movement. Second, deploy application layer gateways with deep packet inspection. This catches malicious payloads hiding inside tool descriptions. Third, run your MCP servers in secure, immutable containers with strict resource quotas so you don't fall victim to exhaustion attacks. Fourth, use host-based security monitoring to catch those sneaky in-memory attacks that bypass the network. And finally, utilize enhanced OAuth 2.0 Plus with sender-constrained tokens, ensuring identities absolutely cannot be spoofed. But hey, locking down the server infrastructure doesn't mean much if you're just inviting malicious tools right through the front door. Because tools in MCP are dynamic, potentially executable entities, implementing a rigorous vetting pipeline is absolutely critical. You want to prevent the integration of inherently insecure utilities. This means doing static and dynamic analysis, setting up a structured approval workflow with multiple stakeholders, and demanding mandatory periodic recertification. And once a tool is actually approved, we have to manage its behavior. We basically have to treat tool descriptions as potentially executable code. That means applying strict schema validation and sanitization. But we also have to monitor them continuously for deviations using Yara rules and behavioral baselining. If a tool that normally just queries a local database suddenly tries to establish an outbound network connection, the system needs to catch that runtime anomaly instantly, using AI-powered detection models to spot novel poisoning techniques.
Section 4. Client-side security controls. Let's shift away from the server for a minute, because if the client is compromised, well, the whole chain of trust just completely breaks down.
Never trust, always verify. In a dynamic AI ecosystem, traditional network perimeters are practically obsolete. Just because a request comes from inside the network doesn't mean it's safe. This demands a strict zero-trust model. Every single access attempt from every single client has got to be verified continuously. So the crucial point here is eliminating standing privileges. You should literally never give an AI model permanent access to a sensitive tool. Instead, we use just-in-time, or JIT access. You grant access to tools only for the exact duration of that specific task. Decisions need to be context-aware, looking at things like the time of day or device posture, and there must be a real-time mechanism to instantly revoke that access if any suspicious activity pops up mid-session.
Security in this context is definitely not a one-time login checkpoint at the start of a session. It's a continuous validation framework. Every single MCP request needs authorization. The research heavily emphasizes making cryptographic code signing mandatory for all tools and storing them in secure, immutable registries. And of course, strict input schema validation, enforcing data types, formats, lengths, is fundamental to stopping parameter smuggling and injection attacks right in their tracks.
Section 5. Securing multi-server deployments. Let's see how all of this builds when we deploy multiple MCP servers across a massive enterprise environment. Because, let's be real, you aren't just running one of these.
Scaling up introduces entirely new trust boundaries. If you have an AI talking to 5 different servers, you require absolute isolation between agent sessions to prevent cross-contamination. You need centralized, on-the-fly secrets management, which means absolutely no hard-coded API keys anywhere. And you have to implement cryptographic server authentication. When a client requests a tool, it must cryptographically verify that the server hasn't been spoofed to steal credentials.
Section 6. Challenges and final takeaways. Implementing this level of comprehensive, enterprise-grade security is necessary, sure, but it definitely comes with some substantial real-world hurdles.
Security architects really have to balance these stringent controls against potential developer friction and system usability. For example, doing deep packet inspection and complex cryptographic validation on every single request, that can introduce some serious performance latency. Furthermore, vetting third-party tools is incredibly resource-intensive. And because MCP is still relatively new, we're currently facing a massive gap in empirical validation for some of these novel attack vectors.
But despite those challenges, the paper's conclusion is absolute. You cannot treat MCP security as an afterthought. You can't just bolt it on later. It has to be woven directly into the fabric of your AI governance strategy from day one, covering the whole shebang, from the network layer right up to data and identity. So, as you empower your AI models with external tools and blur the line between digital intelligence and physical execution, you really have to ask yourself, are your AI integrations secure by design? Are your defenses truly ready for this wild new frontier? Because the tools are out there and the AI is ready to use them. It's up to us to make sure they do it safely. Thanks for joining me on this explainer, and I'll catch you on the next one.